All right, welcome back, everybody. I hope you enjoyed your lunch and feel reinvigorated for this afternoon. So it's a great pleasure for me to introduce Ruiping. She worked as a lecturer at the Institute for Advanced Studies in History of Science at Northwestern University in China. And her work has been focused actually on the work of William Thomson. And she was co-supervised by Tom Archibald and Simon Fraser in Vancouver, somebody I know very well. So I know she's been extremely well supervised. And she's also become, recently she's become interested in digital humanities as well. And she's going to talk to us about Thomson's work on general hydrodynamic equations based on the notes. So over to you, Ruiping.
Hello, everyone. Today, my report topic is Thomson's work on general hydrodynamics equations based on the notice. About the notice, I will introduce in the slides. Okay. In the translation from the hydrostatics to the hydrodynamics in the 19th century, around the middle of 19th century, there have an important problem about what form of the mathematics equation can be express the state of the fluid in motion. This is become the goal in the middle 18th century. There have many mathematicians and the mathematical physics do a great contribution to this problem, such as all of these famous person, Bernoulli and D'Alembert, and all of especially the first two persons, they based on the different principle, but this principle, such as Bernoulli's conservation of Lie force, there has a connection with the conservation of the energy later, and the Euler and the Laplace and the Lagrange. So obviously these people give the simple or the basic equation about to express the state of the fluid in motion. But these mathematical results, however, still did not accurately explain real fluid problem. This is a complex problem. Basic equation form of the fluid dynamics as well as boundary conditions has not been adequately understood. So how to provide a more general equation and the boundary condition satisfied by these equations. So after this, just now we mentioned these persons in the 1811 and 1830. This is a same book, just the two editions. Poisson explored the general equation of hydrostatics and hydrodynamics and analyzed certain surface conditions. However, Poisson himself admitted that his result cannot be applied in some certain cases. He told us in his book. After him, there have many British mathematicians and mathematical physics based on his work to do some contribution about the general equation and the boundary conditions. So there have Thomson and Stokes. They do some, especially Stokes, but Thomson, maybe the 1847 to 1848, he and Stokes write 6 papers for students notice on hydrodynamics public on this famous journal. So but we know in reduced to calculation of the fluid motion, there had two sorts of the equations. One is general geometry equation, and the other is the dynamic equation. Geometric equation in order to express the connection of the particles in the system of fluid in motion with the curves of the surface, and the other equation about the dynamic equation to express the force and the first introduce the motion, the force and the motion relationship. So Thomson in three papers, in three notices, talk about the geometry equation based on Poisson's work and general Poisson's work. So about the Stokes or dynamics equation, he talked about in the other three papers. So today I mainly focus on Thomson's work. So this report purpose to look at the difference between Thomson and Poisson. Because in these three papers, he, especially the first two papers, he, for the Poisson's result, he write this notice. So, how did Thomson rethink the Poisson's result and based on what? So, firstly, I need to introduce Poisson's some work in that book. This is a second edition of that book, Treatise of Mechanics, in 1833. This is the second edition. In the sixth book, in second volume, Poisson discussed the general equations of the movement fluid. About the general equation. Okay, this is his some from the article 647 to 51. He based on the property of the all direction of the force of pressure in all directions is equality, and consider this the ABCD and introduce components of velocity, hydrostatic equation element dm in movement fluid. Yeah, left the equations about in the book, he gave the general equation in hydrostatics, and then he introduced the component of velocity, so have the general equation hydrogen because the flow in moving, so there have the velocity. So this is this equation is not enough. He consider the other things and instead of the u prime. So the second equation becomes the third. So far the general equation obtained, but there have the 4 unknown functions, so need to another equation combined with the third equation to express the general equation. So and then Poisson consider two types of fluid, compressible and incompressible. So in the fluid is compressible according to the mass must always remain the same. That means conservation of mass, and then have the another equation 4. This is the first equation, and then if the fluid is incompressible, the 4 becomes the 5, have the 2 times. So the third, the equation 3, equation 4, all equation 3 and equation 5 as a general equation for the 2 type of the fluids. We know Laplace told us the according to the Mariotti law, this difference between the hydrostatics and the hydrodynamics. In the hydrostatics, all the direction the force is equality, but in the hydrodynamics, it can just Poisson knows this principle, but he just still use the all the direction of the force is equality. But here he consider the temperature influence the fluid. So there have the equation 6 and 7 to express the temperature in the influence in the two circumstances. So there have the two system equations. Poisson provided the in different cases. Equation 3, 4, 7 for the homogeneous liquid, and for the air or any gas, there have the equation 3, 4, 6. This is the general equation Poisson gave in his paper, in his book, and based this work, Thomson and Stokes do many works on the hydrodynamics. And the important part in the Poisson book, he express the equation for y is a continuity equation. This is here we can understand the Poisson's the principle. In other words, how he considers the fluid as what? This is a translate. So this is the translate number 651. First he told us why the equation 4 is a continuity equation. He thinks the fluid is how to say it's a layer, many layers. And he mentioned in the book, he told us that if the and then he gives the cases in which case the continuity equation is applicable, in which case the equation 4 cannot take place, because but if heated from the bottom, there has a vertical cylinder, and he thinks if heated from the bottom and the liquid will alternate moving, so that means the fluid is not continuity. So the equation 4 cannot take place in this case. So this is a picture I draw on the user software. Here he consider the fluid is many layer. So if the heated from the bottom, the liquid will move in not in the same direction, is up or down and alternately. So equation 4 does not take place in this kind of movement. Why Poisson emphasizes continuity and believes that the fluid must follow the continuous motion in order? In his book, anywhere he this is just an example. He considers the fluid as a level layer. This layer successively moving, not alternately. So although Poisson gives the general equation for movement of fluid, he approaches fluid motion from a macro viewpoint. He believes that in certain situations, it's as a melted random moving and blah blah. So how did the people afterward handle this problem? Thomson and Stokes do a lot of work. Stokes' work, I have read an English paper published in Chinese journal. So today we do not talk about his work. In the sixth notice on the on hydrodynamics, the first, second, and the fifth written by Thomson. The first one is on the equation of continuity. The continuity I mentioned the Poisson, and the second one is the equation of the bounding surface. Yeah, this talked by Poisson. Thomson just based on his work to general Poisson's result. And the fifth is vis viva of liquid emotion. In this paper, he just used analytic and price the vis viva, similar like the conversation of energy. Yeah, this is Kelvin. Yeah, starting from the perspective of the conservation, mass, energy, and the Thomson and the Stokes work are starting from the perspective conservation, mass, energy, supported by the kinematics, and emphasize on establishing mathematical and physical models. This reflects the mathematical style of Victoria area, but also specifically Thomson's style. So in the 19th century, in British, Thomson and Stokes work on the hydrodynamics, especially the method and the mathematical method and some physical idea developed the hydrodynamics in the 19th century in British. Okay, this is Thomson's work. So in this book, in this paper, he talked about Poisson's work in that famous book, Treatise of Mechanics. So the first notice on hydrodynamics about on the equation of continuity. He reconstructs the general equation, different from Poisson's result. And in the footnote, he said Poisson admits that proof which he gave is inapplicable to certain conceivable circumstances of fluid motion, but this case use his continuity equation can be dealt with. So this is a first paper. In similar like Poisson, he consider about this equation and about the bounding surface equation, but he instead of the varying space, but choose a fixed space S. And depend on the relationship between mean density and the quantities. Mean density, just only this way, mean density can deal with a Poisson, general Poisson's work. So, and in the first page, he said the equation of continuity and is generally applied to all cases of fluid, but not like the Poisson said, in some special cases, this equation cannot be used or applied in this case. But Thomson told us the continuity equation as applied to all cases of fluid motion, no exception. So yeah, this is by myself drawing the picture. So it's very simply. He introduced the mean density and the quantities content, just a conversation of the mass. They depend on the same principle, I think. So the density, quantity, and in the from the time t to the t plus dt, the quantity is it remains the same quantity. So you based on this, he have the two a b, so a equally to b, and has a first one equation. Meanwhile, he deal with a finite space I is bounded by the fixed surface, and finite interval and not the infinite time t to t plus dt. Now finite the interval of time t1 to t2 instead of infinite dt before. So here he also think that the mass always constant. Under this suppose give the analytic process to verify the fact above. And this is introduce the integral. Yeah, I think in this paper the important work, mathematics work, Thomson introduced is a direction constant of a normal LMN, and then to express the equation 3. So he gives a total quantity lost from the space S between this time. There have the and then integral second a times 4 is the total equations. So here he proves that M1 equal to M2. Here I think the important work is that he used the direct cosine of normal to use through the integral idea to express the mass equal to mass in different time. Yeah, and then as the other case, if the fluid is incompressible, the density proof is invariable, and there have this equation. So summarize, Poisson approaches fluid motion from macro viewpoint, consider it as a multitude of randomly moving molecules with interview gap that are discontinuous in space. But Thomson approaches fluid motion from macro perspective, avoiding the intervening space between the molecules and treating the fluid as a continuous mass of fluid. So this is the difference between them. And he think this, just in this way, the continuous equation can be applied in all cases. So generally, we consider the fluid in motion to express the state of the fluid in motion. So expect the equation, the continuous equation, and need to combine with the equation of certain surface condition in the various problem hydrodynamics. So in second note, Thomson again do some work different Poisson on the problem. In the article 652, Poisson he considered the certain conditions of surface, especially considering the relationship between the points in the fluid and the surface of fluid. He thinks the points always remain on a fixed or mobile wall, or which belong to the free surface. That's the geometry equation. That means express the particle, the relationship between the particles or points in the fluid with the surface. So Poisson's work relating to the surface equation, the motions under the consideration are subject expressed by the following equation. So when he consider the surface equation, he gives examples and gives the surface equations f, t, x, y, z, and so on. So he thinks if the different time, the same point move from here to there, but the points satisfied the surface equation. And he gives two circumstances at the free surface of a liquid. And the first case is on the fixed, in the case of a fixed wall. Second case is at the free surface of a liquid. Thomson's work relating to surface equation. So this is a part, second part, notice on the hydrodynamics, on the equation of the bounding surface by the Kelvin. So here is the footnote. The condition to be expressed is entirely equivalent to this, that the surface must always contain the same fluid matter within it, and it therefore appears that, and so on. So he said, Poisson had justly remarked that cases may actually occur in which this condition is violated, but we cannot infer, as he and the subsequent author have done, that the differential equation is liable to exception in its application. See Poisson. So Thomson thought Poisson's work is not very general. He needed to rethink his work, his result. He considered the fixed space S, and its bounding surface will always be such that there will be no motion of the fluid crossing. He thinks that if the fluid is moving and there has how to say A, B, C, D, that and there has no motion flow into it or flow out it, so the quantity is keep constant. So the differential equation expressing this condition is as well as that varying surface bounding, or for the varying surface. So this equation can be satisfied. And similar like the first notice, he introduced the normal motion of the surface at any part to find this equation. I think this is his mathematics method in the hydrodynamics. It's very, yeah, there has a same surface moving in the time from time t to t2 from the p prime is the same point. So he thinks the normal motion of the surface is the projection of p prime on normal of the surface. So, and use some mathematical method, such as Thomson equated the length of gradient vector of the surface to the length of the normal vector, and then consider the projection one vector on the other vector. There has the result. So it's either get the bounding surface equation like this, different from Poisson's result. This equation expresses the fact that mentioned above, that every particle of the fluid remains on the same side of the surface. So in order to illustrate this equation, he exploit can be applied to the cases, but Poisson excluded. So he tried 3 different ways to express the motion particle, the relationship between the fluid particle with the surface curve. Yeah, the first case is line of motion lie entirely on the surface ice. And the third and the second and the three. So the second and the three, that means there have a cylindrical portion of fluid and with bounding surface ice as B plane, and they will have a thin line between them, and the fluid do a circle moving and then go back the cylindrical. And the third case is that a spherical portion of the fluid with whatever the form of the ice. So that means he thinks that all of the fluid will go back in the cylindrical or some. So this is a case is he gave, and I draw the picture related to the second and the three, and he said the Poisson, the proof that the continuity equation of the surface ice, all the abundance surface equation cannot apply in some special cases, but Thomson said, oh no, this can be applied in every circumstance. So this is a summary concluding remarks. Poisson from the molecules view imagine the fluid is have many layers. And he gives the continuity equation. This is a very important work because the later mathematician, based on his work to explore the in actual hydrodynamics, but he thinks there have some distance within the fluid, so it's not a continuity. But the Poisson consider the three different surfaces in a free wall or the fixed wall or the free surface and so on, gives a different surface equation. It's very complex. But Thomson used the mean density. He must have to use the mean density, mean velocity, and the quantity to substitute the Poisson's the three factors. So the mathematics method and in Thomson introduced a normal motion of the surface and the other methods in the paper. So compare the two persons' work, we can see the transfer processes from macro to micro in 19th century, and Thomson's mathematics work and conversation of energy idea influenced the British mathematical physics in 19th century. The third notice on the wave, I forgot the name. There he that use the mathematical result to express the conversation of the energy. So I don't need to show here. So that's the Thomson's three notice on the hydrodynamics based on Poisson's work, and the Stokes based on Poisson's work do another equation, dynamic equation. So that's Thomson's work. Okay, thanks. That's my.
Thank you very much for really illuminating talk on Thomson's work on hydrodynamics. So questions, we have time for questions. Stella.
Thank you. Sort of midway through your slides, you mentioned that in rewriting Poisson, Thomson's work both embody the style of the Victorian era, and then in particular his personal style. And I wondered if you could ambiguate that a bit. What was specifically Victorian versus Thomson in the way he was rewriting Poisson, and perhaps if Stokes used a different style then, because he was still Victorian, but then not Thomson.
You mean the Thomson's is not the Thomson's
So you,
personal style?
yeah, his personal
Yeah.
style versus the Victorian style of the era.
Yeah, because I just focus on his mathematical physics work in the 19th century. That time maybe it's not very it's not right, but I think the Thomson and Stokes, their idea and the mathematical mathematics method is the leader in the Victoria realm. They influence many people in Victoria that time. So just his idea and the method have the influence. And many people based on Thomson Stokes' work to develop the do other contribution. So maybe it's the whole Victoria area the style, not just his self style. So yeah.
Thank you.
Okay. Thank you.
Any other questions? Yes?
When we teach the continuity equation, we usually use the Reynolds transport theorem. So when did that come into play? It looked like what you wrote down is what you would get if you did something like the derivative with respect to time of the mass of a blob of fluid. And you take the d by dt inside and you end up with the conservation equation. So when did that happen?
Sorry.
I'm thinking about there's something called the Reynolds transport theorem. Do you know that?
The Reynolds transport theorem, do you know that? Maybe. Yeah, okay, all right.
I don't know when that came into play.
Yeah, maybe somebody else knows that.
I think definitely after Stokes, I mean, certainly.
I think it comes later, but I'm just wondering, I mean, when you look at the formulas that you showed from Thomson's continuity equation, right? This is how you would get that nowadays. I think if you were teaching students, this is what you would do. You would think of a mass of fluid contained in a volume that can move around. And then you say that the mass is conserved, and so you have the time derivative of the mass of fluid in a moving volume has to be zero. And to take the d by dt inside, you would use the transport theorem. That's how I would teach it if I was teaching it.
Yeah, just maybe just a quick point of clarification there. So, I mean, this in some sense interesting to see that what they're representing here is what I would call the local formulation of conservation laws. Correct. What you're describing is the macroscopic.
Yes. But it's usually the global version. Usually easier to think of it in the global.
And so in some sense, that's an interesting question of which is the more natural route. If you learn enough about differential forms, then indeed you might actually argue this is an advanced way of doing it. So, but my question relates to this tension between the microscopic and the continuum. So you're emphasizing the Poisson with the molecular view, and William Thomson had this continuum view. But in some sense, Thomson was also thinking about the atomic theories of matter long before everyone was convinced. So he had this theory of crystal structure long before people were convinced. So he did have an atomic view in mind. And that's quite evident when you look at the so-called Gibbs-Thomson effect, which is the role of surface tension. Surface tension is explicitly needing and requiring the atomic nature to be present. So I'm just wondering, in this lineage of his thought, if you come across this coupling of bulk continuum theory, which is what you're discussing here, volumetric physics, and its interaction with interfacial physics, which is this Gibbs-Thomson relation. So have you come across in your research threads of this thought where interfacial physics meets bulk physics?
Sorry.
Yeah, okay, and maybe, yeah, okay, so it's a difference between the bulk, what's happening in a kind of bigger situation, and then what's happening at the surface, the difference between sort of in the main, and then at the difference between the surface where you need to think about at the molecular level, whereas here, if I'm interpreting you correctly, that this is where he's thinking in the sort of macroscopic, which is the argument you have put forward there. So do you see anything in what Thomson did in the microscopic at the surface, what was going on in the surface level with surface tension in the fluids?
I think he considered the fluid as a whole, but he do not care the macro.
The microscopic.
Yeah, he don't think the fluid have the so how to say distance the gap. Yeah.
Yeah, I mean,
Maybe
it's historically, to think of this comment, the Gibbs-Thomson relation came much later, so maybe at this point of writing.
He's thinking in those terms,
He's
and
thinking
then,
in those terms and maybe later.
Okay, I have one question, Ruiping. So you showed the 6 notes, 3 by Thomson and 3 by Stokes.
Yeah.
I haven't looked at these notes, so I don't know. So were they written sort of in conjunction with one another? Were they working together to write these notes?
Yeah, in the you mean the between the Thomson and the Stokes?
Yeah, so you showed
the
6 notes,
notes.
3 by Thomson, 3 by Stokes, and I was just interested in how they came to write the 6 notes. Were they working together to write those notes?
In the Stokes paper, the note, maybe the first note, in the footnote, he told us, he said, they write the notes, 6 notes for the students. There have some a little new things by them, but they didn't published in other where. So I think they just for the students and
It was a collaboration.
It was a collaboration, yeah, okay. All right, I think we're kind of running out of time. Thank you very much again, Ruiping, for a very interesting talk.